want to measure the rate of reaction, we want to know what change is happening to either the reactant or the product. So one way of looking at rate would be the rate is change in concentration per unit time. Now this change, if it is in reactant's concentration, it will be negative. So rate will be negative, which basically means that it is decreasing, the concentration is decreasing. Similarly, if it is about the product, then product will be made more, which means change will be positive. But in all of this, how do we measure this change? Now, for that, we don't always have to measure concentration, because it turns out that rate can be indicated by any change that is happening in a reaction. Now, there are many things that can change during a reaction, not just concentration, and based on how they're changing, we can figure out the rate. So these factors, the things that keep on changing during a reaction, could be temperature, volume of a gas produced, mass of reactants, or the product, of course. The only way in which mass will change is if a gas was produced and allowed to go out. So that's an important idea. Then, of course, there's concentration. There's also pH that may change. So basically, anything that changes during a reaction can be used to figure out rate of reaction. So we have different instruments to measuring this. So to measure the change in temperature, we use thermometer. To measure the change in volume, we use a gas syringe. To measure the change in mass, we use a balance. For concentration and for checking pH, we can use different machines, connect them to a computer, and use different data logging techniques to figure out the change in concentration and pH. And this we study later on in A levels. Sometimes we don't even want to measure the change in temperature, we just want to get a rough idea. And that idea, we can get it by visual inspection. So I'll quickly go over how these factors can be used. So let's suppose there's a reaction in which you have, let's suppose there's a beaker, and in that beaker you have acid solution. In that, you add magnesium powder. Now this is magnesium solid. Now a couple of things can happen. Magnesium, when it reacts with gas, it will release gas. That gas, if you allow it to escape, then the change that you can measure is the change in mass. So what you can do is that you can basically take this thing, put it on a balance, and measure the initial mass before this thing happens and the final mass. Now, a good idea to do this reaction would be to, instead of using a beaker, we could do this reaction in a conical flask. The advantage of using a conical flask is that you can, so instead of having this, we could use a conical flask. And the advantage of using a conical flask is that you can plug it with cotton. So you have magnesium in there and all that. But this loosely fitted cotton will make sure that any air is not going to come in, or any gas from the air is not going to come in and dissolve in an acid solution and all that. So now you will get a change in the mass. You will measure the initial mass, the final mass, and in fact, you can even measure the change after a certain interval of time. So you could maybe make a table, and in that table, you have time on one side, and that could be in at 0.0 minutes or seconds, you're getting that, and at 60 seconds, you're getting that, and at 120, you're basically measuring them after regular intervals, and you will get mass in grams based on this. Now, this value will obviously decrease because the gas is allowed to escape. And then what you can do is that you can draw a graph of this thing, and because the mass is decreasing, the mass is the dependent variable, so mass goes on the y-axis, time goes on the x-axis, and notice that I'm writing the units with them. It starts at a certain value, you put that, then you put another one, then you put another one, all the values as you go, and then you plot them with on a graph. It will reach a certain value at the end, but it will not reach zero because the mass is never going to be zero, because you have the conical flask, the acid solution, even the product that you have, and the funnel and everything on the road. Now this curve that we're getting, you can measure the gradient of this curve, and you will notice that the gradient is basically y2 minus y1 over x2 minus x1, which in other words is basically you're going to pick two values on the graph, measure the change in them, and we use a triangulation method for that. Now this triangle, compared to if I were to pick these two, this triangle, compared to if I were to pick these 2 points, this triangle, you can notice that the slope is decreasing. So the slope indicates rate. So we can see that initially the rate is much faster, the particles are colliding faster, they're reacting faster, but as the time goes on, the particles are not reacting as much or as frequently, which is why the rate is decreasing. Another reason is that all the reactants are eventually used up, which is why the rate becomes zero at the end when it's a flat line. Now, similar reaction, but a different factor that we could still use is if I were to collect the gas produced in a gas syringe. So I have a gas syringe. Now notice that this gas syringe should be graduated. These markings should be there so we can measure the gas that is produced. So we do the same reaction. There's magnesium in the acid solution, but this time we just make sure that it's not a loosely fitted cotton there. In fact, we plug the funnel completely. Why? Because we do not want gas to escape otherwise. Now this gas syringe will measure the volume. Now whenever you draw the diagram in the exam, label the important bits. So for example, I'll label this as magnesium, this is acid solution, and this is conical flask, and that is gas syringe. So conical flask to show where we're collecting this. Now we will measure the volume that is collected. So now we will still have time in seconds or minutes, and we will also have volume of gas. And this volume can be in cm cube or dm cube. So we take that, we get the values for different intervals of time, different values for volume of gas. We do this reaction, and then we graph the values again. And this time, because gas is being produced, the graph will actually start at zero, because initially you have zero gas that has been made. But after a while, the gas will be produced and you will get a graph like this, which will resemble roughly this shape. And this graph will be basically increasing, but it will also become flat after a while. The reason it becomes flat after a while is because this is the maximum volume that has been produced, and after that the reaction stops. So on the x-axis, I have time in seconds, and on the y-axis, I have volume in centimeter cube. Now again, we can use the gradient formula or the triangulation method to pick any two values here, draw the slope, find out the slope, do the values here, do the values here, and you will again see that the slope is decreasing, which means the rate is decreasing as the reaction progresses. And it's the same case that happened before. The reason is simple. Reactant particles are being used up as the reaction proceeds. We could also do this same thing by measuring the change in temperature. And this time we could actually use a beaker. So I have acid, I have the magnesium in there. So this is magnesium ribbon that I have, and this is the acid solution. And now when I put the magnesium ribbon, to measure the change in temperature, I will need a thermometer. Just make sure the thermometer is there and you are constantly stirring the solution to make sure that the heat is constantly distributed. The thermometer should not be touching the base of the glass or the walls of the glass beaker, because we want to measure the temperature of the solution. Now, because there can be a loss of heat, we have to make sure that there are two precautions that we must take. Number one, to reduce the loss of heat, we should have some way of lagging the sides of this container. So that's first thing that we should do. Second, using a lid would also make sure that you're not losing a lot of heat. So to minimize heat loss, so first thing is that the thermometer should be immersed to 1/3 of the solution. That's one way to make sure that you're measuring the temperature. So that's the depth that you must try to cover. And secondly, to minimize heat loss, by using insulation, lagging, and lid. Lastly, you need to make sure that the external environment does not affect or interfere with the results. So the temperature of room or lab should be constant. That's something that we should do. Now, in this case, we will obviously do the experiment, measure the change in temperature, and the temperature will rise or decrease depending on whether it's endothermic or exothermic reaction. This reaction in particular is exothermic. And more importantly, we will also know that all reactions will eventually come down. The temperature will come back to the room temperature eventually. So you will see a nice change in the temperature like that. So if I'm measuring the time in minutes, for example, and there is the temperature, we use a capital T for that, and degree Celsius is usually the unit that we use in lab. So this will obviously give us different values, and we will draw the graph based on this. Now, initially, your graph will be a straight line because you are going to get the room temperature initially, and suddenly there will be a huge jump, a huge spike in the temperature if this is an exothermic reaction, or a huge spike again. It's falling down if this is an endothermic reaction, and you will see that it reaches a certain level, a certain temperature, and then it starts to wane and eventually go down to the room temperature again. Now, in this case, you will basically be seeing three lines. You will see one horizontal line for the initial room temperature that you have. Then there will be an increase, which we usually show by a straight line or a straight upward line or a curve going up. So, for example, you could have a line going like this, or you could have, depends on what the values are, but you could also have them graph like that. Sometimes the examiner doesn't want us to draw a graph like that. They want us to draw straight lines. So they ask us to draw a vertical line somewhere on the graph when you added the values, and then they connect the values of temperature as it fell down back to the room temperature. So if I do that, and I have to make sure that I draw a straight line which is best fit. To draw a best fit line, you must make sure that the points above and below the line are exactly the same. And wherever they meet, we assume that that point is the maximum temperature that was reached during a reaction. Okay, and over here I have temperature, and here I have time in minutes. Lastly, we do measure rate of reaction by visual inspection. For example, if I'm doing a reaction in a conical flask, I mix two solutions, and this solution is providing a precipitate. So there's a precipitate that will occur if a reaction continues to form. Now, what we can do in such a scenario is we can have a piece of paper or a tile with a cross mark on it. Now, the beaker on top, initially you will look into this, and you will be able to see the cross mark. But as the reaction progresses and more precipitate is made, for example, if the reaction is producing sulfur, then more and more precipitate will be made, and then you wouldn't be able to see the cross mark through the solution. So then you measure the time taken for the mark to disappear, and you repeat the process multiple times by changing concentration, by changing the amount of reactants to figure out how long it takes for the mark to disappear. And these different reactions will obviously tell you, how fast or slow these reactions were based on the changes that you do. Remember one thing, in all the reactions that we measure the rate, we just change one factor, either the temperature or the concentration or the surface area or the pressure, any one factor, or the catalyst, any one factor. But we have to make sure that all the other factors remain the same, and we have to ensure that we take all necessary precautions to ensure that, because that way our results will be more reliable. And that is how you measure the rate of reaction in a lab.